You know that feeling? You're hammering away on an app or a website, everything's loading instantly, and then bam! Suddenly things just crawl to a halt, or maybe you get slapped with an error message like, too many requests. It feels like the internet just decided you've had enough for today. And chances are it kind of has. What you've probably run into is a rate limiter doing exactly what it's supposed to do. It's not personal, really. It's there to protect the service and, funny enough, other users too from getting completely overloaded.
Okay, so it's not just me being impatient then. There's actually a system behind that wall you hit. But why do services even need these limits? I mean, why can't I just request whatever I want whenever I want? Seems simpler.
Yeah. That's the fundamental question, isn't it? And it really boils down to sharing resources. Think of a server like a really busy restaurant and kitchen, right? Everyone's putting in orders. Those are your requests. Now, if one table suddenly orders like 50 dishes all at once, the kitchen gets totally swamped. The wait time for everyone goes way up, and maybe the whole operation just grinds to a halt. Ah, so that's the noisy neighbor problem I've heard about.
Exactly. In a digital system, that's one user or maybe one application making way too many demands, hogging the CPU, memory, or network bandwidth.
And it basically ruins the experience for everyone else.
Precisely. And it's not always someone being malicious. It could just be a script that's misconfigured and looping accidentally, or maybe a bug causing tons of retries, or honestly, even just a legitimate spike in traffic that this system can't instantly scale up to handle. So rate limiting is really a defensive thing. Keeps things stable, available, and fair for everybody.
Okay, this is actually pretty fascinating. We had a listener share a whole bunch of sources, technical articles, looks like some research papers, design docs, maybe all about rate limiters. They want to go deeper than just knowing they exist. They want to understand how these things are actually built. From the basic rules up to the really complex stuff, like making them work across a huge distributed system.
That sounds like a great mission for this deep dive. Let's unpack the core ideas from these sources. We can look at what makes a good rate limiter, the functional stuff, and maybe more importantly, the non-functional requirements. We should explore where you actually put it in your system architecture. That's a huge decision. Then we can get into the clever algorithms they use for counting requests, because it's not as simple as it sounds, and definitely tackle the big challenges of making it all work reliably when you've got, tons of servers involved.
All right, let's jump right in then. If you're building one of these, what are the absolute basics, the must-haves? Functionally, what has to happen?
Well, based on these sources, the most obvious thing, the core function, is just enforcing a limit. It has to reject requests from a client if they go over some predefined number within a certain time window. So you set a rule like no more than 10 requests per second or maybe 1,000 requests per day, and the limiter just enforces it.
And I assume those limits need to be flexible, like different rules for different people or different parts of the service.
Oh, absolutely. Configurability is totally key. Service owners need really granular control. Maybe your premium users get higher limits, right? Or super sensitive endpoints might have much stricter limits than, say, public read-only ones.
And the person making the request, the client, they need to know they've hit the limit. Yeah, you can't just drop their requests silently.
Exactly. Clear feedback is crucial. The standard way, especially for web stuff, is sending back that HTTP 429 status code. Too many requests. It's basically a universal signal that means, okay, you've been throttled, you need to back off for a bit.
So those are the what it does things. Now, what about the how well it does it, the non-functional requirements? This sounds like where the real engineering challenges pop up.
Yeah, this is where the rubber really meets the road in system design. And the most critical one, often kind of overlooked maybe, is low latency. Think about it, if every single request coming in, good or bad, has to pass through this rate limiter check. Well, that check itself can't add much delay. If your limiter adds even, say, 50 milliseconds of latency, your whole service just got noticeably slower for everyone. The goal is usually aiming for sub-millisecond added latency.
Wow, okay, so the rate limiter itself can't become the bottleneck it's trying to prevent. That's a key insight right there.
Absolutely. Then, naturally, there's scalability. As your service grows, from thousands to millions of users, your rate limiter system has to scale right along with it. It needs to handle that increasing volume of checks. Usually means scaling horizontally, adding more machines as needed.
And availability. What if the rate limiter system itself goes down? Does my whole app stop working?
High availability is definitely important, but the sources seem to really emphasize this strategy called fail open. Basically, if the rate limiter has problems, maybe it can't reach its database or something, you stop throttling. You just let the request through, maybe with some very basic local limits as a backup. instead of failing closed. Failing closed would block all requests, even legitimate ones, causing a total outage. So failing open is usually better.
That makes a lot of sense. Risking a bit of potential overload for a short time is better than a complete blackout. It's an availability-first approach during failure.
Exactly. It's a trade-off. Accuracy is also important. Of course, you don't want to block good users by mistake. And finally, just how easy is it for other teams, other services in your company to actually use this rate limiting system? Ease of integration matters.
Okay, so we know what a good one needs to do and how well it needs to perform, but before you can limit someone, you have to figure out who they are. How do you identify the client you need to apply the limit to? That feels like it might not be super simple.
It's definitely not simple. The best way to identify someone really depends on the kind of traffic you're dealing with. Like for users who are logged in, using a user ID is pretty ideal. It lets you set very precise per user limits. You can say, okay, this specific user gets X requests per minute.
Right, like limiting how many times I can make a post or something.
Yeah, exactly that kind of thing. But the obvious downside is, well, it only works if the user is logged in. What about your public API endpoints, or the login page itself, or just anonymous users browsing? Plus, a determined attacker could just create a whole bunch of accounts to get around a simple per user ID limit.
Okay. So what about IP addresses? That feels like the default for anonymous traffic.
IP addresses are very commonly used for that, yes. You limit requests per IP. The big challenge, though, and the sources point this out clearly, is that an IP address doesn't always map neatly to a single user. You could have lots of users sharing one IP, think everyone in an office building, or on a public Wi-Fi, using NAT. So if one person at the coffee shop starts hammering your service and hits the IP limit,
everyone else at the coffee shop suddenly gets blocked too, even if they were doing nothing wrong. Ouch. That's the dark side of IP limiting.
That's exactly it. And the flip side is true too. One single user might appear to come from multiple IPs. Maybe they're on a mobile network, using a VPN, or just have a dynamic IP that changes. This makes IP addresses less reliable for tracking individuals and carries that risk of unfairly penalizing legitimate users.
Okay, so user IDs are good for logged-in users, but easily bypassed by creating more accounts. IPs work for public traffic, but can unfairly block groups. Is there anything else, maybe for, business partners using an API?
Yeah, for B2B stuff or developers using your platform API keys or tokens are very common. Each developer or partner gets a unique key. This allows for very specific limits tied directly to that key. And importantly, they're easy to revoke if there's abuse or if a key gets compromised. The downside, of course, is you need a whole system just for managing these keys, generating them, distributing them, validating them alongside your regular authentication.
So the insight here seems to be that identifying the client isn't a one-size-fits-all solution. Relying on just one method is probably asking for trouble, either through abuse or collateral damage.
Precisely. The most robust rate limiters tend to use a combination of methods. You might start with IP-based limiting for just raw incoming public traffic. Then, once a user logs in or provides an API key, you switch to limiting based on their user ID or key. You might even apply multiple rules at the same time, like maybe a generous global limit per IP, plus a stricter limit for each specific authenticated user coming from that IP. And dealing with sophisticated bots that try to mimic humans across lots of IDs and IPs, well, that's an ongoing battle. Often needs more than just simple counting.
All right, so once you've figured out who you're trying to limit, the next huge decision is, where does this rate limiting logic actually live in your system? Location seems critical.
It's a really fundamental architectural trade-off, yeah. The simplest place, conceptually, is on the client side, like your mobile app just counts its own requests.
Yeah.
But as the sources say, that's completely insecure. A malicious user can just turn it off or modify the code.
Yeah.
So for any real enforcement, that's a non-starter.
Right, okay. That's more like a polite suggestion than actual protection. So where does it go on the server side?
Well, one option is putting it server-side, but local to the application instance itself. The rate limiting code runs directly inside or right alongside your main application process. The big advantage here is speed, extremely low latency. Because there's no extra network call to check the limit, it happens right there. It also means, initially at least, fewer separate moving parts to manage.
That definitely sounds fast. What's the catch?
There are pretty significant downsides, especially when you start to scale up. First, it uses the application server's own resources, its CPU, its memory, just to process requests that you're probably going to reject anyway. So if you get hit by a big flood of requests, the rate limiter logic itself could actually consume enough resources on that local server to slow it down or overwhelm it even before it rejects the traffic. Also, scaling your rate limiting capacity is tied directly to scaling your application servers. You can't scale them independently. And any state the local limiter keeps track of, like current counts, is usually lost if that specific server restarts.
Okay, so fast, but it eats application resources and doesn't scale independently. What's the alternative? The more centralized way.
The other main strategy is to place the rate limiter as middleware, or more commonly, as a dedicated service that sits in front of your application servers. This could be built into an API gateway, or it could be a completely separate, scalable service. All incoming requests hit this first before they even reach your actual back-end logic.
So this acts like that protective shield you mentioned earlier.
Exactly. That's the key advantage. It shields your core back-end servers from getting hammered by excessive traffic. Bad requests get stopped and rejected before they consume resources on your expensive application servers. This dedicated service can also scale independently. Its scaling needs are driven by the sheer volume of incoming traffic, not necessarily how many application servers you have behind it. And it gives you one central place to manage and enforce all your rate limiting rules, even if you have dozens of different microservices.
Makes sense. The trade-off then must be performance, right? Adding that extra step for every single request.
It is. You're adding an extra network hop for every single request, whether it's legitimate or not, compared to running the logic locally inside the application. So you're making a classic system design choice here. You're trading off that little bit of extra latency, putting it in front for much better protection, resource isolation, the ability to scale independently, and centralized management. Most large-scale systems tend to opt for this distributed in-front approach, even with the small latency costs, because those other benefits become critical for overall resilience.
Fascinating stuff. Okay, so once a request hits the rate limiter, wherever it lives, how does it actually do the counting? How does it keep track over time? This is where the algorithms come in, I guess. It can't just be a simple counter, can it? Because of the time window aspect.
Definitely not just a simple counter, because yet time windows are tricky. The core job is tracking requests within some kind of moving time frame. And different algorithms tackle this with different trade-offs, mainly around accuracy, how much memory they use, and how they handle bursts of traffic.
Let's start with what sounds like the simplest one mentioned in the sources, the fixed window counter. How does that work?
Yeah, conceptually, this one's super straightforward. You define a fixed time window, let's say 60 seconds, and it's aligned to the clock, like from 1.000000.59. The next window is 1.0, 1.0 to 1.0, 1.59, and so on. You just have a counter for the current window. Every time a request comes in, you increment it. If the count goes over your limit, you reject the request. Then at the exact start of the next window, say 1.0, 1.0, you just reset that counter back to 0. Simple. Uses very little memory.
Simple, low memory, but the sources point out this boundary problem. What's that about?
Right. That's the big weakness. It's all about the transition point between windows. Let's say your limit is 100 requests per minute. A user could potentially make 100 requests right at the end of one window, say at 1.0, 1.59, and then immediately make another 100 requests right at the start of the next window, maybe at 1.0, 1.01. So they've actually sent 200 requests within just a couple of seconds, right around that minute mark. That's double the intended rate and could still cause a nasty spike in load.
Okay. So simple, but it allows these bursts right at the edges of the time windows. What's a more accurate way to handle the sliding nature of time?
For pure accuracy, the sliding window log is probably the best. It literally keeps a log, usually sorted by time, of the timestamp for every single request that came in within the current window duration. So if your window is 60 seconds, it stores the timestamps of all requests in the last 60 seconds. When a new request arrives, you first look at the log and remove any timestamps that are now older than 60 seconds from the current time. Then you just count how many timestamps are left in the log. If that count is over your limit, you reject the new request. Otherwise, you add its timestamp to the log and let it through.
That sounds like a true sliding window then. No boundary problem because you're always looking back exactly 60 seconds from now.
Correct. It perfectly enforces the rate limit over any sliding 60-second period. The major drawback, though, is memory. You have to store a timestamp for every single request that falls within that window. If your limits are high, like thousands of requests per minute, or your time window is long, maybe an hour, this can end up needing a lot of memory.
High accuracy, but potentially very high memory cost. Is there something in between? Better than fixed window, but less memory hungry than the log.
Yeah, there's a hybrid approach called the sliding window counter that tries to strike a better balance. It uses counts from two fixed windows, the current one and the previous one. When a request comes in, it estimates the count for the true sliding window. It does this by taking the count from the previous fixed window, multiplying it by the percentage of that old window that still overlaps with the current sliding window time frame, and then adds the count for the current fixed window.
Okay, wait, that sounds a bit more mathematically involved than the others.
It is a bit, yeah, and its accuracy kind of depends on an assumption that the requests in the previous window were spread out relatively evenly. So it's not quite as perfectly precise as the log method, but it does smooth out that hard boundary problem you get with the simple fixed window. And crucially, it's much, much more memory efficient than storing every single timestamp. It just needs 2 counters. It's a pretty clever compromise.
Interesting. What about these bucket algorithms I read about, like token bucket? How does that one work?
The token bucket uses a really nice analogy. Imagine you have a bucket, and it has a fixed capacity, say, it can hold 100 tokens, and this bucket gets refilled with new tokens at a constant rate, maybe 10 tokens drip into it every second. Now, every incoming request needs to take 1 token from the bucket to be allowed through. If there's a token available, the request takes it and passes. If the bucket is empty when a request arrives, no token for you, the request gets rejected.
I like that analogy. It feels like it could handle short bursts of traffic quite well.
It can. That's one of its main strengths. If the bucket happens to have accumulated tokens, because maybe traffic was low for the last few seconds, then a sudden burst of requests can consume those available tokens and get through right up until the bucket is empty, or up to its maximum capacity. It's also very space efficient. You basically only need to store the current number of tokens in the bucket and the timestamp of when it was last refilled. Because of its ability to handle bursts smoothly, it's cited really often as a good choice for general API rate limiting. The main design challenge is just picking the right bucket capacity, which determines your max burst size, and the refill rate, which sets your average allowed rate.
Makes sense. And the other bucket algorithm, leaking bucket, how is that different?
The leaking bucket kind of flips the analogy around. Imagine requests themselves are like water being poured into a bucket. The bucket has a certain size. Now, requests leak out of the bottom of the bucket at a constant fixed rate like a steady drip. This output stream is your processed requests. If the bucket is already full when a new request arrives, water pours in, that new request usually gets dropped, or maybe put into a queue if there's one.
So its main effect is to smooth out traffic, turn bursts into a steady flow.
Exactly. It's excellent for taking spiky, unpredictable incoming traffic and turning it into a nice, consistent output rate. That could be really good for things like queuing systems or maybe processing streaming data. It's also space efficient, similar to the token bucket. However, unlike the token bucket, bursts don't just pass through if there's capacity. They tend to fill up the bucket, which might cause subsequent requests to be dropped or delayed if queued. Tuning the parameters, the bucket size, and the leak rate is also really important here.
Okay, let me try to summarize the algorithms then. Fixed window. Super simple, low memory, but suffers from those bursts at the window edges. Sliding window log. Perfectly accurate, no boundary problem, but can use a lot of memory. Sliding window counter. A clever hybrid, much better on memory than the log, smoother than fixed window, but maybe slightly less precise. Token bucket. Uses the token analogy. Great for allowing controlled bursts, space efficient, popular for APIs. Leaking bucket. Uses the water analogy. Great for smoothing traffic into a steady flow, also space efficient, but bursts might get dropped or delayed. So they all represent different points on the spectrum of accuracy, memory usage, how they handle bursts, and maybe implementation complexity.
That's a really good summary. That covers the main algorithms you'd consider from a single server perspective. But like you hinted at earlier, the real complexity, and honestly where these sources seem to spend a lot of their time, is making all this work consistently when you have a distributed system, across many, many servers.
Right, because if requests from the same user, say me, are hitting different servers in your backend, how does server A know what server B just counted funny?
That is the absolute core problem of distributed rate limiting. If your overall limit for me is, say, 10 requests per minute, but my requests happen to land on 3 different servers, if each of those servers is just using its own local counter, each one might think, oh, I can handle 10 requests from this user.
Mm-hmm.
So you could easily end up allowing 30 requests in that minute before things catch up.
Yeah.
You absolutely need a way for all those servers to coordinate and agree on the total count for each client.
And I imagine trying to update the same counter from multiple servers at the same time must be a complete nightmare. Race conditions everywhere.
Oh, absolutely. If 2 servers both try to update my counter in some shared place at the exact same microsecond, well, a simple read the current value, add 1, write the new value back operation can easily fail. One of those updates could just get lost. Server A reads 5, server B reads 5, server A writes 6, server B writes 6. The count should be 7, but it's only 6. That's a classic race condition.
Okay, so that's bad. What are the solutions then? How do you get consistency and coordination across all these different rate limiter instances?
Well, the main solution highlighted across the sources is using some kind of fast external shared data store to hold the rate limiting state. Think things like the counters, the token counts, maybe those timestamps for the sliding log. A very common choice here is an in-memory store like Redis because it's really fast. But just having a shared store isn't enough because of those race conditions we just talked about. You need atomic operations.
Atomic operations. Can you explain what that means in this context?
Sure. It means that the sequence of actions needed, like checking the current count against the limit, and if it's okay, incrementing the count must happen as a single indivisible step within the data store itself. So even if multiple servers try to do this exact operation on the same counter at the same time, the data store guarantees that it processes them one after another sequentially, not interleaved. This prevents those lost updates. Redis, for example, has built-in atomic commands like incr, increment, or dcr, decrement. Or, more flexibly, it lets you run small Lua scripts directly on the server, and those scripts execute atomically, so you can script that check-then-update logic safely. This atomicity is absolutely crucial for accuracy in a distributed setup.
Got it. So shared store like Redis plus atomic operations to prevent race conditions.
Yeah.
What else is needed for a big system?
Well, as you scale up, even a single fast Redis instance can become a bottleneck if all your rate-limiting checks for all users are hitting it. So sharding the data store becomes essential for both performance and scalability. Instead of one giant Redis holding every counter, you partition your data. You might divide up the clients based on, say, a hash of their user ID or their IP address, and store the counters for different sets of clients on different Redis instances, shards. This spreads the read and write load across multiple machines and reduces the contention on any single counter or single Redis process.
And how do you make sure requests for the same client always go to the right shard to find their counter?
That's typically handled using consistent hashing. It's an algorithm that helps map a client identifier, like user ID, to a specific shard in a way that minimizes disruption if you need to add or remove shards later. It helps ensure that, most of the time, requests for the same client land on the same shard where their counter lives. This makes lookups faster and simplifies things.
Okay, shared store, atomic operations, sharding with consistent hashing. But wait, hitting an external store? Even a fast one like Redis on every single request. Doesn't that bring back the latency problem we talked about earlier?
It absolutely can, yes. Even a fast network round trip to Redis might add a millisecond or two, which might be too much for some super high performance requirements. This is where you start seeing hybrid approaches or optimizations. For example, you might keep a local cache on each rate limiter instance. For the counters of very frequently seen clients, the hotkeys. Check the local cache first, only go to Redis if it's not there, or the cache value is stale. Or, another approach is for servers to track counts mostly locally, but then periodically sync those local counts up with the central store. This dramatically reduces the calls to the shared store and lowers average latency. The trade-off is that you might briefly exceed the global limit during that sync interval. You sacrifice a little bit of perfect, real-time accuracy for better speed.
That makes sense. It's another trade-off. Strict consistency versus performance. Now, thinking about that shared data store again, what happens if it fails? If your main Redis shard holding my counter goes down, does rate limiting just stop working? Do I get blocked?
That's where fault tolerance becomes absolutely critical. You can't have your entire rate limiting system depend on a single point of failure. The sources really emphasize using replication for the data store. For Redis, you might use its built-in replication features, often in a single leader setup. You have a primary instance handling rights, and one or more replicas mirroring the data. If the primary fails, one of the replicas can be promoted to take over, hopefully with minimal data loss.
Okay, so redundancy for the data itself. What other safety nets are there?
Well, that fail open strategy we discussed is key here too. It's a fault tolerance mechanism for the rate limiter service. If the limiter instances detect they can't reach the shared store, maybe the connection times out or they get errors, these should be designed to switch into a fallback mode. Instead of just erroring out and potentially blocking requests, they might temporarily disable throttling altogether, or maybe apply some very high, simple local limit just as a basic safety measure. Patterns like the circuit breaker pattern are often used here. The code trying to talk to the shared store wraps the call in a circuit breaker. If calls start failing repeatedly, the breaker trips and immediately redirects logic to the fallback mode, like fail open, for a period without even trying to hit the failing store. This prevents hammering a dead service and allows for quick recovery.
Ah, so the circuit breaker acts like an automatic safety switch. It detects the store as unreliable and quickly switches to the backup plan, protecting the overall system from getting stuck.
Precisely. It prevents cascading failures, where one failing component drags everything else down. And remember sharding. That also helps with fault tolerance. If one Redis shard goes down, it only affects the clients whose data happens to live on that specific shard. It limits the blast radius of the failure, keeping the rest of the system working. Scaling this whole distributed system horizontally then involves adding more rate limiter service instances and potentially more data store shards, using that consistent hashing to rebalance the load.
Wow, okay, so building a distributed weight limiter is way more involved than it looks. It's shared state, atomic operations, sharding for scale, consistent hashing for routing, replication for data safety, and then fallback strategies like fail open, often managed by things like circuit breakers to handle failures gracefully. That's a lot of interacting pieces.
It really is. And that's where a huge amount of the engineering effort goes for these big, high-scale services. It's a classic distributed systems problem.
Okay, so let's say the system works. The decision is made either, yep, this request is allowed, or nope, too many requests. How does the system communicate that decision back to the original client effectively? We mentioned the 429 status code for too many requests. Is there other info it should provide to be helpful?
Yes, absolutely. The sources highlight the importance, especially for APIs, of including informative HTTP response headers along with that 429. Some standard ones you often see are X-rate limit, which tells the client what their actual quota is for the current time window. Then X-rate limit remaining, which tells them how many requests they have left in this window, and X-rate limit reset.
And X-rate limit reset.
Yeah.
That tells the client when their count will reset back to the full limit.
Exactly. It's usually either a Unix timestamp indicating the exact time the window resets, or sometimes just the number of seconds remaining until the reset happens. Another really useful header, often sent with a 429, is retry after. This explicitly suggests how many seconds the client should wait before even attempting their next request. This helps prevent them from just hammering the server immediately.
These headers seem crucial. They basically allow clients, especially automated scripts or developers building against the API, to be smarter. They can implement intelligent backoff and retry strategies instead of just blindly hitting the server again and again, which only makes the problem worse.
Totally. And coupling these helpful headers with really clear public documentation is vital. The docs should explain the rate limiting rules, what the headers mean, and how clients are expected to behave when they receive a 429. It's all part of creating a good, predictable developer experience.
Okay, we've covered the design, the algorithms, the distributed headaches. How do you actually keep a system like this running smoothly day to day in a production environment? What are the operational considerations?
Yeah, operations are key. Visibility is always paramount. You need really robust monitoring in place. You absolutely need to track things like the total number of requests hitting the rate limiter system, how many requests are being rejected, globally, maybe broken down per client type or per API endpoint, what latency the rate limiter itself is adding to requests, and of course the resource usage of the rate limiter instances in that shared data store, CPU, memory, network, I/O.
And I assume setting up alerts based on that monitoring.
Definitely. You need alerts for things like sudden unexpected spikes in the number of rejected requests, could indicate an attack or a major client-side bug. Alerts for any degradation in the rate limiter's own performance, like increased latency. And certainly alerts if there are problems with the shared state store, connectivity issues, high latency, resource exhaustion. These are critical for detecting problems early, whether it's a fault in your system or maybe some kind of abuse you need to investigate. Those fault tolerance mechanisms we talked about, replication, failover, fail open, they're designed to help the system automatically ride out many kinds of issues. But the monitoring and alerting tells you when these mechanisms are kicking in or warns you if a problem is bigger than they can handle.
Makes sense. One last piece. How do your actual application services for things being protected, how do they use this rate limiter? Is the limiting code built into every single service, or is it somehow separate?
The sources discuss a couple of common patterns for integration here. One way is to embed the rate limiting logic directly within each application service, usually as a library or maybe framework middleware. Which is usually the absolute lowest latency because the check happens right there in process. The con is that it's usually language or framework specific. You need to maintain rate limiting libraries for every different tech stack your company uses. And upgrading the core rate limiting logic means you have to redeploy every service that embeds it. It's tightly coupled.
Right, tightly coupled. What's the alternative? Something more decoupled.
The other popular pattern, especially in microservice architectures, is the sidecar or daemon approach. Here, the rate limiter logic runs as a completely separate process, but usually on the same host machine as the application service it's protecting. They communicate over the local network interface, localhost. So the application service makes a very quick local network call to its dedicated rate limiter sidecar, basically asking, hey, can this request proceed based on the rules?
Ah, that sounds much more flexible.
It generally is. It's language agnostic. The sidecar can be written once, maybe in a high-performance language like Go or C+++, and then any service, Python, Java, Node, whatever, can talk to it over that local connection. It allows you to deploy, update, and scale the rate limiter logic completely independently from the application services. It also isolates resource usage. If the sidecar gets busy, it doesn't directly consume the application's CPU or memory. The downside is that local network hop, even though it's very fast over localhost, it's still an extra step compared to an in-process library call. And it adds a bit more complexity to your deployment setup. You now have two processes to manage per service instance instead of one.
So the sidecar pattern seems great for environments with lots of different languages, or when you really want that independent scaling and deployment for the rate limiter logic itself. Both library and sidecar are viable, but the sidecar feels more modern for microservices.
Absolutely. It fits well with the idea of externalizing cross-cutting concerns, things like rate limiting, but also maybe observability, service discovery, security, into these sidecar proxies that run alongside the application code.
Wow. Okay. We have covered a lot of ground here. We started with just understanding why rate limiters are even necessary, protecting those shared resources, dealing with the noisy neighbor, preventing overloads, and recognizing that super low latency is this crucial, maybe non-obvious requirement for the limiter itself.
Yeah, and then we dug into the challenge of just figuring out who to limit, going beyond simple IPs or user IDs. We saw the big architectural choice. Put the limiter locally in the app for speed, or put it out front as a dedicated service for better protection, isolation, and central control, that core trade-off.
Then the algorithms. From the simple fixed window with its edge problem to the super accurate but memory-hungry sliding window log. And the clever compromises like the sliding window counter, and the bucket analogies, token bucket for bursts, leaking bucket for smoothing.
And finally, diving into the really thorny issues of making it work reliably across a distributed system. Using that shared state, needing atomic operations, scaling out with sharding and consistent hashing, ensuring fault tolerance with replication, and having smart fallback strategies like failing open, often orchestrated with circuit breakers.
It's really clear now that building a solid rate limiting system, especially when you're operating at scale, is far more complex than just counting requests. It's a serious piece of distributed systems engineering, but it's absolutely essential for keeping online services resilient, scalable, and fair to all users. It protects the platform and makes sure legitimate users get a stable experience.
It truly is. It touches on so many fundamental system design challenges: consistency, availability, scalability, latency, fault tolerance. It's a fascinating microcosm.
So, considering all these design choices we've talked about, the different algorithms and their trade-offs, the crucial decision on where to place the limiter, local versus distributed, and all the complexities involved in achieving consistency and fault tolerance across potentially thousands of servers globally. What do you think, reflecting on all this, is maybe the single biggest, most fundamental challenge when you're trying to build and operate a